So hi everyone, welcome to day 9 of 2 questions of physics per day series. Here we are going to solve 2 questions and let us begin. So here we have a question where helium gas is assumed to obey the Maxwell law for distribution of velocities. The molecular diameter of the atoms of the helium is around 1 angstrom, that is 10 to the power minus 10 meter. 1 mole of the gas occupies 20 liter at 20 Kelvin temperature. You are required to calculate the mean free path of the molecules and the collision frequency given that R is equal to 8.4 joule per mole per Kelvin and Na is Avogadro number, which is 6 something multiplied by 10 to the power minus 23 per mole. So the particular way to solve such question is to at first recall what is the mean free path. So this is mean free path where we have 1 divided by root 2 pi d square n. And here we have d equals to 10 to the power minus 10 meter given in the question. Temperature is T, volume is V. So our next great job is to only calculate the n, which is here number density. N is it number density, that is number of molecules within the unit volume. So simply we can take n equals to n Avogadro number divided by the volume. So we know that volume is also given, that is 20 liters. So it is 20 multiplied by 10 to the power minus 3 per meter cube. That is the way you can convert into the standard meter cube unit. We know that 1000 liter makes 1 meter cube. This is what you need to know beforehand. Na is Avogadro number. So the number density in this case is going to be 3 multiplied by 25 per meter cube. Now we have all the known values and we are just going to substitute, use our calculator and finally get that your mean free path is around 7.5 multiplied by 10 to the power minus 7 meter. Next, you are required to calculate the average molecular speed using this formula. So we know that the average molecular speed is 2.55 R times T divided by the M, which is molecular mass whole under root. Okay, because for the collision frequency we'll need to know that what is the average molecular speed so that you can know the collision frequency. So in that way, when you substitute all the values, you are simply going to get 3.3 multiplied by 10 to the power 2 per meter second. This is simple calculation. You are allowed to use calculator and that is what you are going to use. And now you know that collision frequency will be nothing but frequency is inverse of time. Frequency is inverse of time, and in that way collision frequency will be average or average molecular speed or mean molecular speed, whatever you want to call, and then mean free path. You know that the unit of the average molecular speed is going to be meter per second, and you know that the mean free path is going to be meter, and they are going to cancel out and you are only going to be left with per second, which is the collision frequency. So finally we can settle down with the collision frequency, which is around 4.4 multiplied with 10 to the power 8 per second. Now you know that we can move one step further and you can calculate the mean free path, mean free time as well, and mean free time is defined as something which is inverse of collision frequency. So it is going to be in second because it is inverse of collision frequency, and it is 2.3 multiplied by 10 to the power minus 9 second. So in that way we conclude that mean free path is 7.5 multiplied by 10 to the power minus 7. Average speed is 3.3 multiplied by 10 to the power 2. Collision frequency is 4.4 multiplied by 10 to the power 8 per second, and the mean free time is going to be 2.3 multiplied by 10 to the power minus 9 seconds. And these all characteristics are nothing but the microscopic behavior of the helium atoms under the low temperature and ideal gas condition. Low temperature, why? Because we have the 20 Kelvin temperature only. Now we have next question where the coefficient of viscosity of helium at 27 degrees centigrade is around 2 multiplied with 10 to the power minus 4 poise. You are required to calculate the diameter of the helium molecule using the given data where Na is Avogadro number. You can approximately use it 6 multiplied with 10 to the power 23 per mole. Kb is Boltzmann constant and atomic weight of the helium is 4 gram. Okay, atomic weight, you know that if it is in the gram, it is going to be 1 mole. So we are given a viscosity n of the helium gas and we are being asked to determine the molecular diameter d. The temperature T is around 300 Kelvin, that is, it is the room temperature 27 degrees centigrade. And we are going to use the kinetic theory relation connecting viscosity to molecular mass, average speed, and molecular diameter as follows. So you know that this is very important formula. You should always remember it, and let me tell you, these are somehow related to PYQ. That is why we call it similar question to PYQ, and these are important. So this eta is viscosity as we have defined. Okay, this m is the weight or mass, you can say, mass of the atom. D is the diameter. D is the diameter. Now you are going to find the diameter. So you use that formula, you took out the diameter one side and then you are going to put the required substitution there. So we have this viscosity which is 2 multiplied with 10 to the power minus 4 poise, and whenever you convert that, it is going to give you the SI unit when you multiply 10 to the power minus 5 kilogram per meter per second instead of this whole term. Okay, so you can see that there is some relation in between poise and that SI unit, which can be calculated. We can write that, okay, 10 to the power minus 4 poise is simply 10 to the power minus 5 kilogram per meter per second. Okay, so in that way one poise is going to be 10 to the power minus 5 divided by 10 to the power minus 4 and then SI unit. You know that it is going to be 10 to the power minus 1 SI unit only. So this is what the solution has used. Temperature is 300 Kelvin, and in that way the atomic mass will be would be, we know that we have 4 gram, which is actually it is the molar mass, the mass of the 1 mole. So you took on the numerator, and that is 4 gram in a mole, and the total number of moles, which is 6.022 to be precise. But we can neglect that decimal part. We know that the number is very large, so it won't make any difference, and it is per mole. And I think here we, okay, great, yes, that's correct. So in that way you can have the weight, actually mass, which is going to be 6.67 multiplied with 10 to the power minus 27 kilogram. Now you know that you have the liberty to use Maxwellian distribution by using the average speed, which is 2.55 RT by capital M, or the alternate formula of this is 2.55 KT by small m. So you know that there is some relation in between RT, KB and Avogadro number. Okay, so we know that capital M is nothing but small m multiplied by Avogadro number, and in that way we can find the relation. This is what I am trying to teach you, that okay, even if you don't know the mathematical formula, you can still have the arguments of physics, arguments of mathematics open, so that you can do little bit of learning while solving the question itself. This is the ultimate goal that we learn by solving. Learn by solving. Great. So let us move forward. So in that way, you can try to find the relationship in between that R by M here is equal to KB by a small m, and this capital M could be written as a small m times Avogadro number, which is equal to KB by a small m, and you can cancel out a small m both sides, and you can write that R is nothing but Avogadro number multiplied by the Boltzmann constant. This is how you try to use the um, basic intelligence, basic IQ to just learn while you are solving, so that you don't forget even the most fundamental crude concept, and you can use that whenever needed. So in that way, the average speed is going to be 1.26 multiplied by 10 to the power 3 meter per second. And now you have each and every ingredient ready, like this mass, this average speed, and you can plug this all here along with the viscosity to get the diameter. In that way, diameter will be around 1.77 multiplied by 10 to the power minus 10 meter. So you can simply write it is okay. 1.77 angstrom is the diameter of that particular atom. And here, of course, we have used the Maxwellian distribution, which is evident from this average speed.